Hi there. In this section, we're going to look at an application of derivatives called Newton's method. So it's obviously very old. So let's jump right in and see how to do it. So the idea here is that sometimes we want to just be able to approximate a solution. Or for those of you in computer programming, you want to be able to program a computer to approximate a solution without having to find special characteristics of a function. Just approximate it. So let's say a car dealer offers to sell you a car for $18,000 with payments of $375 a month for 5 years. You want to figure out the interest rate. So obviously we have technology and apps and stuff nowadays, but let's say you just want to ballpark and just estimate it, just get close. So you'd build an equation and you would get that equation shown there. So nobody can solve that equation, but you can approximate it. So you just draw a graph and you can see that, oh, it looks like it's about 0.008. But the only way to get a sufficiently precise solution by graphing is to repeatedly zoom in on the x-intercept, right? So we would have to just keep zooming and zooming and zooming. And that's not really efficient, right? But we can have a calculator. So we're not going to be programming our calculators. For those of you in the computer science field, if you want to program an algorithm in your calculator, or if you want to use Java or whatever to do this, that's fine. I would just ask that you submit a copy of your code on an exam. So a faster alternative is to use a numerical root finder on a calculator or computer algebra system. So those root finders exist. Now you're not allowed to use it on the test. You have to use the method I'm going to show you. Again, if you want to program it into a calculator, that's fine. So it turns out correct to 9 decimal places. The answer to that problem is 0.0076286603. So how do these numerical root finders work? Well, there's lots of ways, but it turns out that this Newton's method that we're going to see, that's about 350 years old, is actually the most commonly used thing by calculators. So the way that this works is you have a first approximation obtained by guessing or from a sketch of the graph. So for these problems, you're not allowed to estimate too closely. Just keep it within, 0.01 or 0.05. There's no way you're going to be able to guess to 5 decimal places. Then we plot the tangent line through the point. So here we have a blue function that we're trying to estimate. And the tangent line, if we use our initial guess, x1, go up to the graph, and then come back down the tangent line, it intersects the x-axis closer to r than we started. As long as x2 is closer to r than x1, this algorithm is guaranteed to work. And then we repeat the process, right? So the idea, the next slide is the equations. Then the process would be go back up to the line, come over by the tangent. Go back up to the line, come over by the tangent. Eventually you'll get epsilon close to r, right? Because this is a function, so it has its own epsilon delta, right? Now to find the formula, we use the fact that the slope of L, right? So slope of the line is the derivative f prime at x1. So its equation using point slope form is just y minus f of x1, that's y2, is f prime of x1 times x minus x1. So this is the slope. This is the, y1, and this is x minus x1, right? So you can see it here, right? Here's x1. You can call this y1 if you want. It's no big deal. So the idea is that we take the height minus the difference in these times the slope, and we look where that intercepts. So the intercept of L is x2. we just set y equal to 0. And so here, if this is 0, we can solve this for f of x, right? And then we solve it for x2. So x2 is a variable. In fact, after we set this equal to 0, x2 is the only variable, because x1 and f prime of x1 and f of x1, those are all going to be given. So we're going to have a starting value. So we have a function that gives us the next x coordinate based on the previous x coordinate. And it's this. As long as x2 is closer to r than x1, this, if we repeat this process, it'll work. So let's go back and look at that again. So we start at x1, go up to here. So where is x2? x2 is the starting value minus the slope of this times the difference, right? And that gives us this. So it's x1 minus the function itself divided by its own slope. Slopes are y divided by x, so it's x divided by y. So this is our second approximation, and we just keep doing this over and over again. And then we'd use the next tangent line. So if we keep repeating this process, we obtain a sequence of approximations that will eventually converge to r. As long as your first guess is good, this process works fine. So what I'm going to do 2 examples, and then I'm going to show you, your ebook has a nice visualization of this, and then I'm going to show you sort of the Desmos calculator version. So here's the formula that we're going to use. In general, if the nth approximation is xn, and f prime of xn is not 0. So if you happen to accidentally end up on a horizontal tangent, this doesn't work. Then the next approximation is given by, so again, that's what we call a recursive formula. The computer guys will know that as a loop. And if the numbers xn become closer and closer to r as n increases, we say the sequence converges. So what we get is a sequence of numbers. And we can see, is this getting closer and closer to some value? So again, it has something like an epsilon delta definition. And it turns out that as long as we start sufficiently close, this method will always work. So you can see that has a limit definition. All right, so let's do an example, and then I'm going to show you some online stuff. Starting with x1 equals -3, find the third approximation, x3, to the root of this equation. So you can graph the function, right, if you want. Now, we're given the first value here, so you don't need to graph it. But if you want to graph it to get some idea what's going on, that's fine. So, and I put a little hint down here, and we're going to use that hint. I'll show you how to do it. You should have been using it for the MPQ function and some other stuff earlier. For problems of this type, it is much easier to input the Newton's method formula for xn into your graphing calculator and use the table to obtain values. You don't need to do any complicated arithmetic by hand on an exam. You're going to see some mega complicated arithmetic in here. Okay? Especially the problems that require 8 decimal places of accuracy. Use your calculator to do the work. All right, so let's go back real quick and just look at the formula here. Let's look at what we need. We need xn. That will, so we're finding x2 because we're given x1. So we need the function and we need the derivative. Okay, so first thing we're going to do is just take the derivative. Now we plug everything into that formula. So the formula says xn plus 1 is xn minus, this is f of xn, this is f prime of xn. Okay? All I'm doing, I'm putting the little xn's in parentheses so that you know that's where we're going to input values. You don't have to use that notation, but I think it's helpful when you first see this stuff. Where am I going to put numbers? Well, wherever you see xn, that's where you're putting numbers. So we're given that x1 is negative 3. So that means n is 1. So we're going to put negative 3 in everywhere we see an xn. And because n is 1, that means this is x2. Crunch that across, and you get negative 4.08333. So it happens to be a nice fraction, but I'm not requiring that you guys use fractions. For problems like this, I think you only need 3 decimal places for your answer. I'm not sure exactly on this one. Just follow the directions. So you're going to, for intermediate calculations, you're going to want to keep quite a few digits. Because if you're rounding too much, it takes too long for this thing to become accurate. And you only have x1, x2, and now we have to do x3. Make sure you're keeping a lot of extra digits. So this is x2. So we plug x2 in this equation. Right? Now, I used the fraction version just because it fits on the screen better. On your calculator, I don't care what you do. And that's your answer. So that is accurate to however many decimal places you needed. I can't remember if this problem is 2, 3, or 4 decimal places. I kept 6. Just round it to the proper number. But sometimes you do these problems repeatedly, and if you're rounding too much, it takes way too long to find a solution. So let me show you what I did on the calculator to make this problem doable. All right. So here's my function, right? Let me get the answers up here. So here's my function, right? So I just go to the y equals, and I'm just going to plug this in, right? So I'm just going to type in x minus fraction, right? Always just build the fraction ahead of time. 1/3 x. That is not 1 over 3x. That's 1/3 x. Plus 1/2. Oh, sorry, that should be x cubed here. Sorry. I'll just overwrite it. So that's 1. Oh boy. Hold on, let me clear that. Let's try it again. So x minus. Oh, should be using my touchscreen. Much easier. All right. So it's 1/3 x cubed plus 1/2 x squared plus 11 over x squared plus x. Oops. Plus x. Okay, so we're just going to input -3 here. Now, you're allowed to type it in by hand if you want, but I am warning you that that is not the way you want to do this. So just type in -3, and there's your answer. And if you need more decimal digits, you can move around inside this screen and just mouse over this. Just move around inside the screen and get as many digits as you think you need. Remember, if you need 3 decimal digits for the final answer, and you copy down these 3 of these and use those in the next part, your final answer might not be accurate enough. Now, we've already got it in the function grapher. So all I have to do is type in that number. -4.083333. Just put as many 3's in as you want, doesn't matter. And again, just mouse over, and you can see that to any number of decimal places accuracy that you need. So, that's very quick. This is not hard to compute. This is the original function. This is the derivative. So you're taking one derivative, putting everything in your calculator. That's it. All right. And that's the answer. Oh, let me full screen this. All right. So that's example 1. Let's move on to example 2. So this is a really different kind of problem. Use Newton's method to approximate the value of the 73rd root of 73. So what is this? What does this mean? How do we use Newton's method to approximate a number? So here's how it works. So I just put all the work up there so you can see it. So Newton's method is used to find roots, so we just rearrange the original problem. So we're trying to find this value, we just call it x. Right? That's what we're interested in, right? And it was the same in the previous problem, right? We were interested in x whatever it was, x3. But here, we don't know how far we have to go in the process. We're just going to call it x. So I raised both sides to the 73rd power, subtracted 73. Now I have a function that I can find the root of. So this is my function. I take the derivative, plug the function in here with an xn, plug the derivative in here with an xn. There's xn. That's what I'm going to put in my grapher. Okay, so let's go ahead and let me get my calculator fired back up here. And I'm going to put this in the y equals now. So the x can stay the same. Oop. All right. So this is going to be x to the 73rd power minus 73 divided by the derivative, which is 73 x. Oh, hold on, I messed up. 73 x to the 72nd power. Now, the question becomes, how do I find where the root is? So what I did is I went in Desmos. Here it is. And I graphed that the original function. So the original function here is x to the 73rd minus 73. And I looked at where it crossed. And so here's 1, here's 1.1. You can do this on your calculator too, but Desmos is nice because you can grab the screen and drag it around. So I said it looks like it's about 1.05. It's about halfway. All right. So when I input my first number then in my table, I'm going to type 1.05, right? And here's my answer. Okay, so let me get Desmos out of here for a sec, and I'll go back to the PowerPoint. So again, I just put all the work up here. So I started with 1.05. Here I'm showing the work, but I actually did it all on the calculator. So look here. I need to keep 8 digits for this problem, or more. So 1.06542702. Now you might think, okay, well, that's no big deal. I could easily type this in. But now I need to keep 8 decimal digits. So unless you want to type all of this in every time, remember, if you type in one number wrong, it could totally mess things up, and I'll show you why that is in a second. So don't allow yourself to goof, right? Just come over here. Oops. Hold on. All right. Let's try that again. Come over here. Now, just type in this number, 1.06542702, and then just hit enter. And look at what you get. You get this next part. So all you have to do is write down 8 digits, input those 8 digits into your calculator, and this is fine. Now, on paper, you still got to write it down this way. But here's the thing, guys. How do I know when this thing is accurate to 8 decimal digits? You have to keep going until you get 2 answers in a row that have the same first 8 decimal digits. And you don't know how long that's going to take. Right? So let's keep going, right? So 1.06126234. So it looks like it's starting to settle down a little bit, but we don't know. Right? 1.06055258. Now you can see we're really close to the answer, right? This says 1.06053492, 1.06543491. So when we input that last one in, right, so we're on X5 here, right? 1.06543492. That was our number in the previous one. Oop, there should be another 0 in there. Sorry. Where'd it go? Yeah, here it is. 1.06054349. You get the same answer back. So that's the answer. And that's how it works. So, again, small typo here. I forgot to put the 0 in here, guys. And so here, so this is the 6th. If I were to type that in, that'd be the 6th one. So it took me 6 tries down the chain to get it to be the same to 8 decimal places. Again, I forgot to put the 0 in here, so it's accurate to 8. And so n equals 6. So it took 6 tries. Not bad, right? So let's look at what that looks like in Desmos. Let's look at the physical process that's going on here and see if we can understand what's going on with this Newton's method. All right, now in Desmos, I can't start at 1.05. The closest it'll let me start, the closest it'll let me start is 1.1. But that's okay. Let's start it at 1.1. And let's see what that first guess looks like. So what we're going to do, the way this is going to work, here, let me zoom way out so you can see it. So we're going to start at 1.1. And this is what's happening. We're coming up from 1.1 till we hit the graph. Up here. Right? So it hits at 1.1, 978, 153. Then we're following the tangent line back down to get x2. Right? Now we do this again. So this one's in orange. Go up, hit the graph, come back down. Then we did it again. Go up, hit the graph, come back down. And again, and again, and again. And you can kind of see how it works. Right? So as we progress this way, we're getting closer and closer. And you can see by this blue one. So the blue one is the last one, or the purple one. Yeah, you can see by the purple one, it's awfully, awfully close. And that's what happened with us, right? We got really, really close. You can just keep zooming in. So it's, 1.0605, here's 1.0606. So you can see that the accuracy we get is pretty good. It won't go closer than this. And that's pretty much what happened with us, right? The way we did. I started at 1.05. Which came in the other direction, right? We saw what happened. We started at 1.05, and then it went high, and then started coming back down again. And so when you guys, you'll have a homework problem that looks like this. Just start it at 1.05, it's fine. In the past, I've had students start it at 1. So let me show you what happens if you start at 1. So look at where we're at. So starting at 1.1, we got really, really close within 5. Starting at 1.05, we got really, really close within 5. What if we start at 1? 1's not very far from here. So what do you think is going to happen? Well, let's see what happens. If we go down here to 1, look at where the tangent slope is going to take us. Boop. Way over here. Now what's going to happen? We got to go all the way up. And it's so far up on the graph. I don't even know if I can get it to show up. It's so far up on the graph. Like, I seriously don't think. I mean, it's in the billions. Right. It intersects so far up here. Yeah, we're in the billions now. Anyway, you get the point, guys. The point is, don't do this. Okay? Yeah, it doesn't even show up. Let me just zoom back in here. So what went wrong? What's wrong with Newton's method? Well, it turns out nothing's wrong with Newton's method. The problem is that if you pick something too far away, because of the way this thing can bounce around, it might take a really, really long time for this thing to work its way back. So if you pick 1, it might take 90 to 100 iterations. Look how slowly this thing's coming back. Don't do it. So you want to pick a number fairly close. So when you do your graph, and you can do the graph on your calculator, you know, you might look at this and go, oh, it's close to 1.06. Fine, type in 1.06. You still got to get accurate to 8 decimal places. Just pick a number really close, but not too close. So again, if you want to start your first estimate at 2 decimal places, great. Please do that. All right, so that is that illustration. Okay, we did this. I'll fix this before I post it. So the one you guys see will look a little bit different. Oh, there was one other thing I wanted to show you. So this is just the thing built into your textbook. This is the Explore and Test. You can kind of goof around with this and just see what's going on. So I picked this function here. So the way this works is you can pick a starting point to try to estimate the root. So this function, sine x minus 0.06x squared, crosses the x-axis twice. Right? It crosses at 0, 0, and then some other point. Let's say we want to find out what this other point is. So where should we start? So if you start here, you can click up on the steps. Just drag up on the steps. And you can kind of see what's happening. Now, the resolution's not real great. You can zoom in a little bit. Right? But you'll see that this thing converges really fast. Okay? So look, our error is within 6 decimal places. So the second column is basically your error. And then this is your x-coordinate here. So within the 4th iteration, this thing is accurate within 6 decimal places. And so what you can do is you can zoom in and out, and you can mess around starting in different places and seeing what does this do to the estimate. So what happens if I start here? See how it took the tangent takes it way off the screen. How long is it going to take to come back? Not long. And then once you're real close, you can see it's really gonna it really, so 10 iterations, right? So that's how it works. So you guys can practice just clicking around in different places. What happens if you click on the wrong side? What happens? So if you click, let's say I'm trying to estimate here and I click on the wrong side. So let's say your estimate's too far away. If the derivative goes the wrong way, there's no way to get back over here. It just bounces around real crazy. Now it'll eventually find something, but it might not be what you're looking for. Right? So look at that. That's just complete craziness. So you want to use a graph to get a good estimate, right? So if this were your graph, oh, not that, hold on a second. If this were your graph and you wanted to, let's say estimate where this is, if you just said, oh, I think it's about 2.68, right? Zoom way in, close enough. This thing is going to be super accurate. 1, 2, 3. Within 3 steps, it's already correct within 3 decimal places. That's about what I expect you guys to be able to do. So if you want to graph it on your graphing calculator, you can use this Explore and Test. You can use the Desmos thing that I used earlier. So all you have to do is type Desmos. You can Google it. It's Desmos Calculator. I can actually put this link in the PowerPoint. I didn't do that, but I'll put this in the PowerPoint if you just want to link to this. And the way it works is you just change. You go up here. It says a function you'd like to find the roots of. You just change this to your function, and then it'll show you the first 5 iterations. Now, in terms of accuracy, you can keep zooming in, but I'm not sure how well you can use this. So if you only need an answer to 4 decimal places, this works fine. If you need it to 8 decimal places, this probably isn't going to be accurate enough. You're going to want to use the numerical method. But I just want to show you that there's lots of options for this. All right, so that's it. So I know that's a lot. There's a lot going on here. Remember, the algebra is not too hard on this stuff. It's the arithmetic, the actual brute force calculations is what's going to give you trouble. So I'll make sure I will add a link to the Desmos graphing tool that I showed you in here. And the other thing I showed you was the Explore It. You can goof around in there and just click stuff and see how it works. So that's it for today. If you guys have any questions, let me know. You can email me or post something in the forum. And I will see you guys next video. Bye-bye now.